Hello, my name is Hayden Rutherford, and I'll be accompanied by my two partners, Dakota Showman and Patrick Myers, and we'll be presenting our Introduction to Feedback Section B307 project. Just a quick introduction to our project is we'll be doing a below the knee or below the hip amputee prosthetic motorized foot because historically amputees have had problems with their gait. So as they walk, instead of naturally rotating as a typical foot does, it's more so of a rigid motion, and that sometimes has negative effects on just their stride, their gait overall. So our project is hopefully going to be minimizing some problems like that for future amputees. The history of prosthetics dates back to Greek times, but up until the 1960s is when they considered the birth of modern prosthetics. So typically prosthetics are usually expensive if functional and inexpensive if non-functional. And I mean, you have a very wide degree from essentially a peg leg like you'd see on a pirate, more so in third world countries, to motorized prosthetics as we are presenting here. And here's just a quick overview of some prosthetics. Here is a more generic basic prosthetic, and here is a more advanced prosthetic with an actual knee joint. So this would be for somebody who is above the knee amputee.
So the idea we had when we were modeling our system is that as you're taking a step forward, your foot and your leg go at a different angle than when you're standing. And what we can do with that is we can take that angle input and run it through our control system and model it as a torque output. That is, your mass rotates about your foot and you get to make your next step.
Alright, so as you can see in the previous slide, any prosthetic leg can basically be modeled as a spring damper system with a point mass attached to the end. And so what we found was a rotational system with a spring and dampener was the best approximation. So because we'll have an input angle at the foot here that will result in an output of a torque, we decided to go with this modeling system. And as you can see based on the impedance model that we have, we're basically assuming that the torque, input angle, as well as the spring and the damper are all basically applied at this ankle joint, and so it's all in parallel. Whenever we applied analysis of the transfer function in the circuit, we found that G of S was equal to 1 over JS squared plus BS plus K.
The basis of our design parameters were based off of this graph right here, which is data collected by the National Library of Medicine during a stride experiment. So for our settling time, how we determined was right here on this graph B, it shows torque applied during the stride. And if you can see right here, this is where the motor starts to kick in and applies torque. And we determined that was about 15% of the total stride time. And we determined the typical stride was about a second and a half. And that led us to about 0.25 seconds for our settling time. And then our rise time was determined right here, where obviously the data first spikes to a peak, and we determined that to be 0.1 seconds, and our percent overshoot was essentially, it just needed to be under 50%, so we don't have a massive torque kicking in as they finish their stride on the ground. We figured 15% was okay, and it still didn't put the patient or the wearer in a negative position.
So whenever we first started assigning values to our system, we wanted to start out by finding out a value for J, and we mainly did that by assuming an average male weight of around 170 pounds and a leg that was about 20% of that person's weight. That left us with 136 pounds for a point mass, and then about a 20-pound weight for the prosthetic leg, which was modeled as a thin rod. This was mainly not for perfect accuracy, but for a reasonable approximation of how the person in the leg would interact. Whenever we did that, we found that J ultimately came out to be about 65.7 kilograms per meter squared, which was a reasonable value. The other two values for K, the spring constant, and B, which was the dampener constant, we actually determined based upon our desired values, our rise time and our settling time. And these are the values that we got, and as we'll talk about a little later on, this ended up working out very well because it meant our system was already based on the design values that would work. Rather than using trial and error to get our system to function, we were able to reverse engineer it, and by these calculations, create a system that required very little tuning once it was finished.
Now we found our spring constant, our dampener constant, and the moment of inertia of the guy using the prosthetic. But we need to figure out how to tune this controller. Well, it turns out when Kp is equal to 1 right here, our output is way smaller than what we need. Turns out it's going to be about 3.5 times 10 to the negative 5 Newton meters of torque. This isn't enough to help somebody walk. But on the root locus, as you can see here, we can move our poles up to about this corner right here. That's where our settling time requirement meets our percent overshoot requirement. And according to our math, that ends up at a controller value of about 45,000. Now we'll talk about this more in the conclusion later, but that controller value is way better than the one we had originally. The general goal of our controller was to maximize output value and also minimize error. We'll talk about error in just a second, but it turns out that increasing our controller to this value, or anything larger, would do that flawlessly. The only reason we didn't go larger is because, as you can see here, it would start going past our percent overshoot requirements, and we didn't want to do that. So speaking of error analysis, here are our results on our error analysis and our stability for our transfer function. First of all, it actually turns out our stability is really nice. Our controller has to be greater than the negative value of the spring constant. Now, we certainly don't want a negative controller value because that would make our torque outputs the wrong way and you'd fall over. So we're trying not to do that. So our system's going to be stable according to Rath-Horowitz no matter what. Now the error is a little more interesting. As you can see here, it turns out the error ends up being K, the spring constant, divided by K plus Kp, which is the spring constant, plus the proportional controller. Now this isn't exactly 0, which would be optimal, but as we increase our gain, like we said we want to, then our error will kind of go to 0. It also turns out that the error due to disturbance is that same equation because of the way the transfer function works, as you can see here. I'd also like to make a note here. If we were to get rid of our percentage overshoot restraints, or make them larger, we could also increase the gain further and lower our error. The only reason we don't want to do that is we do want to stick with our original requirements.
So whenever we decided to actually analyze our final system, we found out that it's a very robust system. It's extremely stable. Our gain margin is actually infinite, which is perfect. And then our phase margin is also extremely high at 102 degrees, which gives us a lot of play with how we want to mess with gain or really any of the other parameters. This is also reinforced by our Nyquist diagram. Although you might not be able to see it, this point here is a -1. The Nyquist diagram never gets to even -5. It's a very stable system. There's a lot of play that's left over. And this actually allows us to have a time delay of roughly 0.097 seconds, which is very reasonable with modern electronics. A time delay in excess of this would be unrealistic. So this is a part of our system that'll actually work well with real-world constraints.
So in conclusion, on our whole design, the math works out really nicely, but unfortunately it's not exactly feasible to implement in real life. I mean, if prosthetics could be made with just a motor in the ankle joint, somebody would have already done that. It turns out the spring constants and the dampener constants we need for our system to work, given our requirements, are way too large to fit on a prosthetic leg. The thing would weigh probably more than me or you. The mathematics, however, in theory, work out incredibly well. We stayed within our constraints, our output was a good, reasonable value, and our inputs between the angles of operation would all give very good outputs. As you can see here, given a 1 unit step input, the output is about 1.5 Newton meters of torque. Now this means if you were to step 15 degrees forward, that means that our motor would apply 30 Newton meters of torque to your body. And this is actually almost perfect for what you want for walking. Because if you're standing with your feet 15 degrees in front of you, you're going to fall over, so you don't have enough torque to hold you up there. But it will propel you to that next stride. So in conclusion, the whole thing works. Our system met our requirements for rise time, settling time, and percent overshoot. If you could build this prosthetic in real life, if you could find the springs and the dampeners to work with our design, the design outputs would work flawlessly.